So we have a little bit of time here before 6:40. If there are any questions now, could be a time.
Hello, I've got some questions about homework one.
Yeah.
For the problem one, the TH suggests me to use the Leibniz rule, and I'm not sure how to apply this rule when the interval is from some function to the negative infinity.
Okay. So let me see. So if I take, so let me start out with something simple, just to make sure we got it. So if I take an integral from negative infinity to, say, x of f of y dy, and I want to compute the derivative with respect to x, do you agree on that this here is going to be f of x?
Okay.
Do you agree?
And do we have time the derivative of it? Oh no, it's just times the derivative of x, and then it's got 1.
Yes. And so if I take the derivative instead from, say, minus 10 to x, f of y dy, what would you get here?
I would say the same thing.
Yes. So then if you do the derivative with respect to x of an integral from, I don't know, minus infinity to, say, g of x, f of y dy, what do we get?
G of x.
We get,
and it should be f of gx, and then times derivative of g prime x. Oh, okay. Thank you.
you think we have a little bit more time if there's another question.
Also for the problem 2 and part 1, the TA asked me about to consider what will happen when I integrate alpha is greater than -1 and less than -1. I don't see that should be a problem. I think as long as it's not equal to -1, then it's okay.
Okay. Well, see if I remember the problem. Okay, so you have a function. So let's start out with a function where you have just -1. So that's this one.
Mm-hmm.
Okay. And so we're integrating, say from 0 to 1. You have your picture, something like this. Right, and you're integrating this area here. And so what do you get when you integrate 1 over x on that area?
Is ln 1 minus ln 0.
Is it finite or is it infinite?
Infinity.
And so then, so the TA is asking you to integrate something when the power is less and bigger than. So let me do 2 of them. So let me do a square root of x. And let me do an integral from 0 to 1 over 1 over x squared. Right? This is the power of a half, and this is the power of 2.
Mm-hmm.
So what do we get here? Why don't we start with the last one first? But look at the picture. How does 1 over x, this is my 1 over x. And now I want the red one. I want the red one to be 1 over x squared. Which one is biggest, 1 over x or 1 over x squared?
1 over x.
Are you sure?
You mean the whole function is bigger, or?
Yes. Which one is biggest? 1 over x or 1 over x squared?
I'm a little bit confused. As x goes larger, the 1 over x squared will get smaller than 1 over x.
Okay. So if I take a half here,
Mm-hmm.
okay, so now we compare 1 over 2 to the power 2 and 1 over 1 over 2. Which of these two is the biggest?
Okay, the left is
Okay.
bigger.
So is it the red one that's bigger or is it the black one that's bigger?
The red one.
Okay. So the red curve is bigger, so it says up here. So what, if 1 over x integrates to plus infinity, what does 1 over x squared integrate to?
Oh, it's still the infinity.
Okay. So we got that case settled. So the TA also wants you to think about this one. What about this one? So now we're going to get, I'm out of colors here, but now we're going to get a function which is smaller than the black one. So now the integral might be finite, it might be infinite. So what is this thing here? So I had hoped that you would have seen in calculus how to integrate the power. Can you find a function that has this thing here as its derivative?
Yeah. 2 square root of x.
And then you have to evaluate at 0 and 1.
So it's 2.
So this thing here is fine, right?
Yeah.
And there you have the cases.
Oh, so if okay. Okay, gotcha.
Okay, let's get started on the class stuff. Okay, so I hope you guys can all hear me. Tonight, so we have been doing the one period binomial model for the first lectures, and so now what's going to happen is we're going to move on, and we're going to start doing the multi-period binomial model. Okay, so let me write a little bit about the multi-period binomial model, and then I'll switch over to my document camera. So the next goal is the multi-period binomial model. And so on a picture, it's not hard to believe what it is, right? So we've been talking a lot about trees that look like that. So we had a time step here, time 0 and time 1, and the way we go from time the way that we go from time 0 to time 1 with the stock is by flipping a coin. So we start out here, we flip a coin, depending on whether the coin comes up tails or comes up heads, we will go either up or down. So the way that we do that is by saying that S1 is defined as S0 times its random variable psi. So now we move on. So we want to have a multi-period binomial model. The binomial means that there are always two options. So the next one is going to be, and the next one is going to be. So we go up here, we flip another coin. So then we can go, we will now have, so if we call the first random variable the first coin flip for psi1, then we will have psi2, this is going to be S1, and then another coin flip. And if we assume that the psi is all take values u and d, then we could go up to S0, and then it could be u squared, it could be S0, and then it could be ud. And if we go down, then we can go up, or we can go down, so we get S0 du and S0 d squared. So we have in a two-period model, we would have two coin flips. And we could keep going like this, so we could have in an n-period model. The way we would do that is we would take the previous stock price and multiply it onto this psi, the nth coin flip. And so we could create a bunch of periods here. So for us, we would have these size sequence here. This is IID. So we need to know what IID means. It means independent and identically distributed. So the independent. So the independent. Okay, what does that mean? So for example, if I were to compute the probability that say psi1 is U and say psi5 is D, the way that I do that, because of the independence assumption, it means that I can just take the product of the two probabilities. So whenever you compute probabilities of intersections and you have independence, it just becomes products. So that's one of the I's in the word IID. And the other one is the identically distributed. The identically distributed. This simply just means that if I look at the probability that psi1 is U, this is the same thing as the probability that psi n is U for all n. So they all have this distribution. Yeah.
Does that mean that if we didn't want to index the psi, like psi1, psi2 up to psi n, we could just write psi because they're identically distributed random variables?
Yeah, no. I mean, the identically distributed, the distribution of them is independent of n. That's correct. But they're not the same random variable.
Oh, that's why. So that's why you have index, because they're okay.
Yeah, it's not psi. It's not like you flip a coin once, and then what it means is that say that the coin flip was a U. It doesn't mean that you're always going to go up.
Right. They're different things happening.
Different things could happen, right?
Yeah.
But the probability of the coin being U and D, it doesn't change over time. So you can either think about flipping the same coin multiple times, or you can think about flipping different coins. I would prefer to think about it as flipping different coins. But these different coins, they have the same probability. They have the same probability of being heads as every other coin has. So the distribution is independent of n, but the random variables are different. You just happen to have the same distribution. I should also say here that you can see that these trees, they grow together, right? Because S0 times U times D is the same thing as S0 times D times U, right? So these two branches here, they combine into one. And so when that happens, so because S0U D is equal to S0 DU, we say the tree is, and this is the word, recombining. So not all binomial models are recombining. You could imagine that you would have these psi's, so psi1 could take the values U1 and D1, and then the next coin could take the values U2 and D2, and so on. So that would be an example. That would be an example of so the non-identically. To follow up on the question I was asked before, if you have a non-identically distributed coin flips, and so that, say, psi1 takes values u and d, so u1 and d1, and psi2 takes values u2 and d2. Right. So if I look at such a binomial model, I'll still call this a binomial model, and I can still say that psi1 this is independent of psi2. This here means this symbol here. This means independent. I could still have the D independent, but if I look at the recombining property, I'll get this as my S0, and then I'll get S0 U1, S0 D1, and then in the next go I'll get S0 U1, and then U2, and then S0 U1, and then D2, and then this could be S0 D1 U2, and S0 D1 D2, right? And now these two could be different. And so when that happens, you're not recombining. So I'll have here an example of a binomial model that doesn't recombine.
Professor, do you mind going over this example again, please?
Yes, of course. Like for us, the binomial models that we are going to be developing, they have this structure I have on this piece of paper. So they are, for us, the size, these conflicts, they are all independent, and they all have the same distribution. But I could relax this last part here, just keep the independence. So I could look at a model that had conflicts. That were independent, okay, so that's this assumption, but they're not identically distributed. So this is an example of something that is not identically distributed because you don't even take the same values. So the model would then be that I get the first stock price by taking the previous stock price, so the constant initial value, and then multiply it on to the outcome of the first conflict. So then I get this column here. And then I'll do the same thing with S2. This is my S0 times psi1 times psi2. And then I get the last column over here. And so if I map out what are the possible values that psi1 times psi2 can take, well, they can take u1 times u2, they can take u1 times d2, they can take d1 times u2, d1 times d2. So there are these four possible values. But before, when u1 was equal to u2, I'll have that u1 is equal to u2, and I'll have that d1 is equal to d2. Then these two values here are the same. And then I really only get three different possible values at the end. So here's an example of something that doesn't have that property. And indeed, I get four different possible values at the end. And so it doesn't recombine. I have more outcomes here. And there are great benefits. There are great benefits to having this recombining property. If you just try to draw out, so if I have recombining tree, so I would have, this is how it would start, and then it will go. So here I'll have one value, here I'll have two values, here I'll have three values, and if I continue, I would have 1, 2, 3, 4 values. So you see, every time you go one step out, you're just going to get one more possible stock price. But if you have a general binomial model, it becomes very different, right? Because I will start out with the one value and then it'll go up like that. So here I'll have one value and then I'll get two values, and then at the next step, I'll get these two and then I'll get these two. So then I'll have four. Whereas the previous one only had three. And then if I go one more out, I can make it even worse. I'll get these two I get these two, I get these two, I get these two, I count them up, I get 8. So you can see the recombining model has 4 possible values at, this is at time what? This is time 0, 1, 2, 3. At time 3, so at time 3, the combining tree has 4 possible stock values, prices. But if you look over here, it's much richer. I have at time 3, the non-combining, the general tree, has 8 possible stock values, stock prices. So the non-combining is significantly more complicated in terms of keeping track of all this stuff. There are many more nodes in a non-combining tree than there would be in a combining tree. This here is the number of nodes. This here is the number of nodes. Are we good so far? Question in the log. Should we pull it up? The question says, in the combining tree, then we are assuming that u is equal to 1 over d. I don't see why. In the combining tree, we are simply just assuming that ud is the same, right? I'm not saying this is equal to, I'm not saying this is equal to 1. I just want these to converge here.
What I meant to say was, like, when you go into periods 2 and 3, if u equals 1 over d, so when you have one up, essentially an up and a down period, that's how you end up back at S naught.
Yeah, but that's not
what I was.
So this I agree with, but that's not the recombining property.
Oh, okay.
That's not the recombining. This is not necessarily going to be leveled.
Mm-hmm.
This can be crooked.
Okay.
It doesn't have to be that this is equal to 1. If you
All
want
right.
to be leveled, then you need it to be equal to 1.
But in the would that be the case for the recombining tree though?
I don't see why. Because no matter what u and d are, ud is always equal to du.
Mm-hmm. Oh, okay. I probably just got confused with something else.
Yeah, we're not demanding. So when I put my marker here, this is like that's, if I want this value out here on the y-axis
Mm-hmm.
to appear here, so that means that my pin has to be flat, right?
Right.
Then I would need ud to be 1. But it's okay if I have a little push upwards, such that here the initial value, it could be like, I don't know what ud could be, like 1.1, something that would take it up a little bit.
Oh, okay.
That would be okay. It's still recombining.
Okay, thank you.
Yeah. So we will be, at least here in the beginning, we're going to be working with recombining trees. And I'm hoping by looking at pictures like this one, you can see that there is a little benefit to doing that. Of course, you have less richness. The model is not as rich as it would be otherwise, but okay. So at this point, we have, so at this point there was a choice to make as the instructor. All right, so we have our 2 textbooks. So at this point, we are in here in the early parts of the thin book, and right. So this, now we're starting to talk about what's in the second 1.2, the multi-period binomial model. And so we could have followed this. We could have done Like he moves down and he does probability on a coin toss space and so on. And he talks about random variables, he talks about conditional expectation, martingales, and all this good stuff. So we could have followed that path. But given that we're going to be doing continuous time finance, given that I've taught this class many times before, I know what's in here. And it's basically exactly the same menu. Sigma algebras, independence, conditional expectations, and so on. This also comes in here. And what's in the thicker book, the continuous time version, this is more general than what's in the thinner book, the one we're currently working on. So then the choice was either we go through what's in the thin book, when we shift over to the thick book, we have to redo it. Or we try to save some time and energy and just get straight to the thicker book and do the more general case. And it's the latter version that we're going to be doing in this class. There are pros and cons with it. So sometimes professors, they want to ease the students into the material a little bit more, and that would definitely have been the first approach where we go through the same material 2 times. The problem with doing that is that we don't have so much time. I mean, normally this course here is really, this is 2 books, this is really 2 courses. So I'm trying to save time so we can actually get some applications that that we would otherwise not have time to do. So it means that today and next time we're gonna be in for a little bit of a ride. We're gonna get a crash course in what's called measured integration. So we need these results so we can do the material that's in the thicker book. So now, so today and next time, there's going to be a crash course in what's called measure and integration. And this is not easy. And I'm fully aware of the fact that students they typically find this material quite difficult. So measure integration, there will be math departments will offer courses. There will typically be a course at the undergraduate level in measure integration, then there will be a PhD level course in measure integration. So we're going to take the parts of these theories that we need to be able to build models in both discrete and continuous time. So today we're going to be talking about this one. This is today, and this one over here, this is next time. So so with the next, how much time do we have? About an hour. In the next hour or so, there'll be a bunch of new concepts, and we'll try to talk about them. But it will require that you do some studying. It's very easy to get lost in this material here because there are new concepts, and it's also at a higher, it's like a more abstract level than what you might have been used to. Okay, so the goal is to look at a triplet. This is called omega f p. There are 3 symbols in here: omega, f, and p. So so we're going to be spending some time talking about each component. So this is a probability triplet. Omega fp. So omega. So we're going to start out with omega. So omega, this is called the sample space. This is called the sample space. It's also called the probability space. So what are good examples of this? Well, the one we had in the one period model was omega could be heads and tails. We had the two binomial, we had the two period binomial models, and then you have heads, 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 tails, tails, heads, tails, tails. We could also have omega be an infinite number of coin flips. So I'll write this as this thing to the power infinity. So that means, so that is, if I take an element omega, so this thing that looks like a W, this here is a big omega. This one here is a little omega. It looks a lot like a W, but that's how the little omegas are written. That is, so I take an element in my sample space, and this element, this will be a string. That is, if I have it in here, we can write, we write omega is equal to, and then there'll just be an infinitely long vector. It'll be omega 1, omega 2, omega 3, and so on. With this omega n, we'll take values that are either heads or tails. It'll be this infinitely long vector of elements. So that could be an example. This here actually comes up, this comes up in our textbook. Let me just show you where it comes up. If you're interested. Yeah, it comes up here in chapter 5 in the random walk chapter. This entire chapter here, chapter number 5, this is based on this particular sample space. The first one we have here, this was what we did in section 1.1. This one here is what we just did. It's an example of a two-period model. So these here are all models that you'll see in discrete time finance. If you move into continuous time, you will see other examples of omega. One that we're going to be talking about today quite a bit is this interval 0 to 1 that's half open to the left. You could also look at omega to be R. Right, so there are a whole bunch of examples. If we were to peek ahead and see what kind of an omega would we be working with in continuous time, right, so this here is all discrete time. This is all discrete time finance. If you were to peek ahead and look at what would it look like in continuous time. So unfortunately, in continuous time, it looks really messy. So the space that we will need, if we were to write down such a thing in continuous time, would be the set. I'll have functions. I'll have functions that go from, say, 0 to 1 into R that are continuous and that have the property that is 0 and 0. So this is a huge collection, right? You take all the functions that you know that are continuous and have the property that at 0 is 0. So this is a space. This is one possible space that we can work with in continuous time. Okay. So we have some examples. At this level of abstraction, omega is a collection of points. Okay, and these points can be quite complicated elements. They can be elements on the wheel line, and they can be like these long vectors, and they can even be an element in omega can even be a continuous function that is 0 and 0. Okay. So then what? That was the first component. Omega was the first component. So this is a collection of points, and we, at this level of generality, we don't really care to specify exactly what set of points it is. It's a potentially very, very large collection of points. What about F? What is F? As you can see, F is this bold. It's an F that's written with 2 straight lines down. So it's a bold F. So F is a sigma algebra. This is funny letter, sigma, right? Sigma. So F is a sigma algebra. Okay, what is that? I'm working here under the assumption that that is a new concept to most of you. F is a sigma algebra. Okay. So that is F is a collection of system of subsets of omega. Okay, so omega was a set of points. And now F is going to be a set of subsets of omega. Okay, so it's not just any arbitrary collection of such subsets, it has structure. It's such a subset which satisfies a number of properties. The first thing it satisfies is that if I take and I consider omega as being a subset of omega, that thing has to be there. Oh, please note the way that I write here. Like I have points. X is a collection of sets, right? So elements inside F are sets. And omega is a set of points, so that's also a set. And so what I'm writing here is that omega belongs to F, even though omega is a huge collection of points. So omega has to be an element inside F. So that's one property. Another property that a sigma algebra must have is that if I take an element, so I take a set inside F, it has to be the case that if I look at its complement, so remember what the complement is, this is omega less than F, this must also be in F. It has to be closed on the complements. And the third and the final property is where this letter sigma here comes from. So this letter sigma here, this has to do with the third property. If I take sets Fn belongs to F for any natural number, well then that implies that if I take the union, of all these sets, I'm going to get something that lives inside F as well. These are the defining properties of a sigma algebra. I should say here, the word sigma, this has to do with taking countable unions. So sigma, if I replace that by if 3 is replaced by, maybe we should call it 3 prime, meaning that Fn belongs to F for n being 1, 2, up to n. N is a natural number, so I will do finitely many subsets. Then the finite union belongs to F as well. So if 3 is replaced by this, we say that this F here is an algebra. And some people even call it a field. There's a question about what does this line mean, this one here. This just means minus. So if I think about this abstract little piece of land here as my omega, right? And then I carve out an F. Then everything that is not inside F, this is over here. Some people write it with this, I can see here is in the comments it says set minus, and that's right. So if you write this in LaTeX, that's the command that you use. But that should not prevent, and it has not prevented people from writing just a minus sign here. Omega minus F. That's fine. So if you're used to seeing this as omega and then just a minus sign, then this is fine. There are textbooks that will use that. So that's what a sigma algebra is. It's an abstract collection of subsets that has a certain property. Okay, so let's look at some examples of sigma algebras. So examples. We can take the biggest sigma algebra in the world is if I take F just to be 2 to the power of omega. Right. So this is the power set. This is the power set. So that is the set of all omegas subsets. So for example, if I were to do the one we had in last week, where we would have omega would be just h and t. In that case, 2 to the omega would be a big collection. You take all possible subsets of this thing here. So that would be, well, ht itself. That's our omega, right? That has to be there. That thing has to be there. Then you take h, and you take t, and you take the empty set. So you take all possible subsets. And this is typically way too big. And I'm hoping we have time for it, but I'm just going to put in a name here. So when we get to it, you can go back and see. So we're going to be talking about, we have time today, otherwise we'll do it next time. We'll talk about something called Banach-Zariski. This is called Banach-Zariski's paradox. And this has to do with this power set just being way too big. So we will have the need to work with something that is significantly smaller than what we have here. Okay, so let's just leave that for now, and we're going to get back to it in a little bit. Another example could be if I take omega to be R, and I take A just some subset. I take an arbitrary subset. Then I could look at sigma. So this is again sigma coming in. This sigma here is the same. The sigma I'm writing here, this is exactly the same as the sigma I'm writing here. That sigma, if I write stuff like sigma of A, this is defined, this is the smallest sigma algebra. This is the smallest sigma algebra containing the set A. Okay, so it's the smallest sigma algebra, so I need to have these three properties, and I need to have A in there. So how would I do that? Well, I would have to put A in there, and then I would have to put omega in there, and then I'll have to put the empty set in there. Okay, so there's no debating whether or not these three sets should be elements inside the sigma algebra, but the question is this a sigma algebra by itself? And so remember, the sigma algebra has to have the properties that you take omega in there, you take F, then the complement has to be in there. I take arbitrary collection, the union of arbitrary collections also have to be in there. And it's the second one that's problematic. The second one is problematic because I need to have the complement of these sets. These should also all be in there. And A's complement is not. So I need to put A's complement in here too. The last set, the last sigma algebra that I'm going to bring up is the main example. If I take omega to be this half open interval, there's nothing special about the way that I'm taking this interval here. I'm just keeping it open to the left and close to the right. There's nothing special about that way of doing it. I could have kept it closed on both sides. I could have kept it open on both sides. I could have switched it around so it will be closed here and open over here. There are 4 possibilities, and somehow you have to settle on doing one of them. And this one here, this seems to have been the one that most books that I've seen have settled on. So I'm just following suit. People refer to these intervals here as standard intervals, open to the left, close to the right, but there's nothing special about them. You could have switched them around too. I'm just going to follow suit and do what most textbooks that I've seen do. So then, the Borel algebra, the Borel sigma algebra. The Borel sigma algebra, this is denoted B, again this capital B, and then of the interval 0 to 1. This is the smallest sigma algebra containing intervals of the form A to B with, so we will have A, B, and 1. So the smallest sigma algebra that contains all such interval, containing all of these, this is called the Borel algebra. Some of you might be enrolled in or have taken a real analysis course. You might have learned what a topology is. So there are connections between the topology, and if you have the standard topology on R, there's a connection between that and the Borel sets. There are many ways, so that's what I'm saying, is that there are many ways of expressing this, this Borel algebra. So there are some questions. So there are some questions related to this Borel algebra. So what's in there? What are the Borel sets? Are there? Do we have that the Borel algebra, the Borel sigma algebra, is strictly included in the power set? So these are good questions. I mean, it's clear here that you can never get bigger, but you could potentially get a lot smaller. And what are the various Borel sets? So what we know is that I'm guaranteed that all these half-open intervals they belong there. But there is a lot more inside this Borel algebra than just these half-open intervals. So here's an example. So here's an example of a set which is Borel, which is not one of these half-open intervals, which is not of the form okay, so how would I create such a thing? Well, let's go back and just remember. Let's go back and just recall, like we have, by definition, the Borel sigma algebra satisfies the three properties 1, 2, and 3. But based upon these three properties, I can do other things too. Like this has to do with complements and it has to do with unions. I can do other things too. If I take two sets, so this is just a note. If I take two sets, A and B, let me just pick them into an arbitrary sigma algebra. Well, then what? Then I'll have that if I take the complement of A, that's going to be inside F. And if I take the complement of B, that's going to be inside F. Then I take the union, that's also going to be inside F. And then I take the complement, that's also going to be inside F. And if I work out what that is, I'm going to get that this is A intersection with B. So you see, not only can we take unions, we can also take intersections. But it's even more true. If I look at A less than B, I can write this as, I think, A intersection with B's complement. So I can also take set differences. So by manipulating the properties that the three properties that I need to check to see whether or not a sigma algebra, that system of sets is a sigma algebra, I can get more properties. So if these hold from those, I can start also taking intersections and I can start taking differences. So I want to give an example of a set, a Borel set, which doesn't have this form. You guarantee that all these sets, by definition, are Borel sets, but there are many other sets inside the Borel sigma algebra. So here's an example. If I take a point, x, some point between 0 and 1, then we claim that that particular point is also a Borel set. That's what we claim, right? And this set, this doesn't have that form. I cannot write a singleton I can't write a singleton as a half open interval. That's not possible. But what I can do is I can write, this is because if I take these half open intervals and I put some space, so I do like, I subtract a little bit and I go up to x. Right, so I have my line 0 to 1. So it's open here, it's closed here. I take a point, that's my x. And what I do is look at an interval that goes down to x minus 1 over n. And then, so x is in all these half open intervals, and as n increases, this half open interval, it moves in this direction over here. I'm subtracting less and less and less. So I'm taking an intersection. I'm taking an intersection of a decreasing sequence of intervals. This is decreasing. And what's left as n gets bigger and bigger and bigger, then minus 1 over n gets smaller and smaller and smaller. At this point here, it moves towards x. And the only thing that's left is my x. And so there I have it, because I have now been able to write the set that I'm interested in terms of half open intervals, and in this case, a bunch of intersections. And that's permissible because if I have sets that are in the Borel sigma algebra, I know that they're intersections. They're also going to be in there. So here's an example of a Borel set that does not have this form. Let me take a little pause there.
Professor,
Yeah.
I have a question. So, when you say Borel sigma algebra and you say Borel set, what's the difference?
Well, I mean, the Borel sigma algebra, elements inside the Borel sigma algebra are the Borel sets.
What's the, did we define the Borel set? What a Borel set is?
So seven. Yeah. So what are the Borel sets? So this is these are the elements in E of 0, 1.
Oh, okay.
The Borel sigma algebra is the set of all Borel sets. And what this here shows is that there are Borel sets that are not of this form.
But the script, the B with the 2 lines means Borel sigma algebra.
Yes.
And the elements in the Borel's sigma algebra are called Borel sets.
That's correct.
Okay.
Yep.
So you used the property of a sigma algebra to generate a set that wasn't of that form, is what we just did.
That's right.
Okay.
So when I'm asking here is what are those sets? What are these elements inside this sigma algebra? Is there like a nice way of describing all these sets? Like what we had here. This is a very explicit description of the sigma algebra. It had 4 elements. We just lined them up. Yeah, the answer is no. There is no simple description of all Borel sets. There is no, you can't line them up. There are infinitely many. I can't write them all down. Then it begs the question, okay, so does that mean that we only have Borel sets, so all subsets of this interval 0 to 1, they can somehow be expressed in one way or another in terms of these half-open intervals. And so the answer here is no. And typically when I get down to here, there's a student that says, okay, so can you please show me a non-Borel set? And then so the construction here, this is the construction. The construction of a non-Borel set. This is hard. It's not impossible, but let me just give you an idea about what it would entail. So here is if those of you that want to go to, typically there are some students that are interested in going to PhD school, and so what would be thrown at you? So if you were to go to a PhD and take a PhD in the math department at Rutgers, there will be a course at the PhD level that will teach out of this book here, Probability with Martingales. And this is not really very far away. In many ways, this book here, Williams, and the one we're doing, you see, is about the same thickness. These two books are really not that far away from each other. But if you flip into Williams, this is a famous book, so if you're interested in probability at a higher level, this is not a bad book, and it's not very expensive. So that's also useful. So if you flip over to the appendix, you see what he starts out with here in the very first part of his appendix to the first chapter is that he gets himself created a non-measurable set. And you can see here again the word Banach-Sarsky comes up. That was the one I mentioned earlier. And so there's quite it doesn't look so complicated. It's like a page worth in here, but there are a lot of like pieces that go in there. It's not so easy to get constructed, and it's not an explicit construction. This is ultimately something like the axiom of choice is what is needed to make this happen. So I won't give you this construction here. If you're interested, you can Google, and there are lots of ways to argue to say that there must be such things. And this is at the root of why do we need to restrict attention from this class of all possible sets to something small. Okay, so instead of spending my time doing this construction, I would rather spend my time talking about this paradox, because this is more perplexing. I would rather spend some time talking about the Banach-Sarsky paradox, because it will also give you an idea about what is it that can go wrong if we insist on working with this very large collection of sets. Okay, maybe before I dive into this Banach-Sarsky paradox discussion, maybe we want to have, are there any more questions? If not, let me just say a little bit about this Banach-Sarsky paradox. I can see we're also running late tonight. So this paradox of Banach-Sarsky is one way you can get a. So let me just say a few words. So a few words on Banach-Sarsky. You should really try to, if you're interested in it, you should try to go on YouTube and see some of these videos that explain this. Another name for this paradox is to so how to create the sun from a sandcorn. This is if you Google Banachowski, or if you Google something like this on YouTube. I shouldn't say Google on YouTube. If you go to YouTube and you search for something like this, you'll see a number of videos coming up. And so the spirit here is how do you take something that is incredibly small, a sandcorn, and how do you create something that is incredibly big from a sandcorn? Okay, so here's what the paradox is about. We're going to be working with R3. So we're going to be having we're going to be looking at R3. So what we're going to be doing is we're going to measure volume. Right, this is R3. I could also measure area. If I measure area, it will be R2, and if I would measure length, it will be R1. I don't know what to call it when we're in R4 or higher, but we're going to be measuring volume, right? So the idea is, this is my lip balm, container. This is an object in R3, and I'm interested in measuring the volume of my lip balm container. And okay, so what kind of properties should we have if I want to measure volume? Well, one should be that whatever volume should be invariant. It should be invariant under translations. Okay, what does that mean? It means that I want to assign a number that I'm going to call volume on this container, and it should be translation invariant. Okay, so what that means is that if I just move it from here up to here, and I measure the volume again, it shouldn't change. It should be invariant, right? So I measure the volume of the bottle here, and I move it up here, I should get the same two numbers just by moving it a little bit. It should not change the notion of volume. So that should be the case. Volume should be, it should be invariant under rotations. Okay, so what does that mean? I have my bottle, I measure the bottle, and then I rotate it. Or put it up like that. And it shouldn't change the number that I have decided to assign as volume. Okay, so that seems plausible. We should, whatever notion of volume we want to have, it should at least obey these two properties. Okay, so here's the paradox. So if we insist on measuring all measuring, so that means, so if we insist on giving volume to all of this 2 to the R3, well, then we have to live with, then we face a paradox. And the paradox is as follows. I take a set, let me take a ball. So this is my ball, keep in mind we are on R3. So this is my ball. What I can do is I can chop this ball up. I can split this ball into disjoint sets. I can split the ball. I can split, let's call it B. So this is the ball. I can split ball into disjoint sets. Let's call them EM, and reassemble reassemble to get two disjoint sets. I can split it into disjoint sets. I can reassemble and get two disjoint sets of each of size ball. So I take the ball, I chop the ball up into a bunch of subsets. I move these subsets around. I glue them back together. Into two balls, each having the same volume as the original ball. So that's what the phrase comes. This is what's behind the phrase. Like, how do you get from a sand corn to creating the sun? Well, you do this procedure a bunch of times, right? So you take the sand corn, you split it, you reassemble it, you get two sand corns. Okay, so then you take and you do the same procedure on these two sand corns, and then you get 4 and 8 and so on. And before you know it, you got the sun out of the sand corn. This here is this is one version of the Banach-Sasky's the Banach-Sasky paradox, and what it means is that if you want to have a notion of volume, so we in R3, if you want to have a notion of volume, and that notion, it doesn't change when we translate sets, and it doesn't change when we rotate sets around, well, then we have to live with this problem down here. And we don't want to live with this problem down here, right? This doesn't make much sense. So then we can either give up on being translation invariant or being rotational invariant, or we can give up on trying to assign value to volume to all subsets of R3. And it's the latter that we're going to do. So there are simply just sets. There are sets. There are many. There are sets in R3 which we cannot meaningfully assign volume to. That's the conclusion, right? So we restrict attention to a smaller collection of sets, and this is these are going to be called the measurable sets. So instead of going all in and trying to get all the sets measured that we have, we're just going to restrict attention to a smaller class of sets. These are the measurable sets or the Borel sets. Okay, so we were now down the list. We had talked about omega, talked about F, and the last piece in the puzzle is this P. The last piece in the puzzle is the measure P. The P is that's the volume. The question is, so there's in the log, like, how are both disjoint sets the same size as the original ball? Yeah, that's the paradox. How on earth, this doesn't make any sense, right? That's why it's called a paradox. That's why it's called a paradox. The tricky part here is I've not said anything about how one should break this ball into these smaller subsets. The problem is that the way that you break the ball into these smaller subsets is using sets that are incredibly ugly. And they're so ugly that they are actually not Borel sets. And then you can glue them back together and you get this ball. I'm not meaning to say that this is something that is easy to create. I'm trying to give you an idea about why is it that we're going through the motion of talking about sigma algebras. Well, we're going through the motion of talking about sigma algebras because if we are just to look at all possible subsets of something like R3, we get way too many sets. We get these sets that leads to these paradoxes that we can create the sun from a sandcorn. And I mean, we cannot have that. Exactly how do you create these disjoint sets from the ball? Yeah, if you're interested in that, I'm happy to provide you with references on where you can find it, but this will take way too much time of our course to do. The last component in the triple is the measure P. So P is the thing that assigns volume, length, and area in R1, 2, and 3. So P is a measure. This is a probability measure. If so, P goes from its domain, which is going to be F, and it takes the values between 0 and 1. Right, so this here, this is P's domain. And this here, this is the codomain. This is a probability measure if what? If two things hold. If it's the case that P of omega, remember omega is always inside M. This gives me 1. And the second part is that if I take sets, if I take a collection of sets, countable collection of sets, the all measurable, then for any such thing, we have that P of this union, any such sets with, you have to be disjoint, Fn and Fm, they are empty for any n that's not M. Right, so they have to be disjoint. We have that the probability of that union is exactly the same. Is exactly the same as the probability of the individual sets. Right, so if we're looking at, as an example, so on this Borel sigma algebra, on this Borel sigma algebra, we set the Lebesgue measure. We set the Lebesgue measure on an interval a to b. This half-open interval is inside the Borel sigma algebra, and we're going to say that this is equal to b minus a. That's going to be the length of the interval. Likewise, if I look at it more generally, so I'll have a1 to b1, union a2 to b2, union a bunch of sets, an to bn. What will I do here? I will say that, well, a1 is less than b1, is less than a2, is less than b2, is less than all the way up to 1. How would I do this? Well, I would say these are all disjoint intervals, so how long, how much length do I have here? Well, I'll take b1 minus a1 plus b2 minus a2 plus all the way down to bn minus an. So here I have given meaning to length when I measure these half-open intervals. But there are, as we know, many more elements inside here than just these half-open intervals. So it begs the question, how do we extend this Lebesgue from these, from half-open, from these intervals a to b to all Borel sets. But we only defined how the Lebesgue measure, how it measures length on these half open intervals. But I also want to know, what about all these other sets that lives here? How do I do that? Okay, that's gonna be next time. So this is next time. We are out of time for tonight. There's a question coming up. It says, are the Borel sets the next largest sigma algebra after the Borel set? So the answer is no. That's not how it goes. So are there bigger sigma algebras we're interested in? And the answer is yes. What we have is we have the food chain. So here we have 2 to this, and over here we have B. And there is something in between here. There is a sigma algebra in here, and this is called the Lebesgue sets. If, for those of you that are really interested in this, you can try to figure out what is the cardinality. What's the cardinality of what you have here? What's the cardinality of what you have here? And what's the cardinality of what you have here? And you can see that these cardinalities, like you have infinitely many, right? So cardinality is about how do you compare infinite numbers. And the way you compare infinite numbers is you put them, you look at, you look at, like, if I am to look at the Borel sets, how many Borel sets are there? Well, they're infinitely many. Okay, so can I put them into a correspondence with, for example, the natural numbers? If I can put them into a one-to-one mapping between the structure I have here and the natural numbers, I'll say it has the cardinality of the natural numbers. So you can try to investigate sigma algebras by computing their cardinalities. And so for the question that was given here, is there something in between that we could be interested in? There is something here. And the Lebesgue sets, they have a higher cardinality in the Borel sets. So the answer to that question is yes. There are bigger sigma algebras that we might be interested in. Then there's a question, is the previous page? This is the previous page. This is what it means to be a probability measure. The probability measure is a map. So a map has a domain and a codomain, right? Well, we need to agree on what kind of things we can put into the function. Well, we can put into this function here, we can put sets that are in the sigma algebra F. Okay, and this spits out numbers between 0 and 1. So such a map is called a probability measure if it satisfies the two properties that P of omega is 1, and that when I take disjoint sets, I can compute the probability of a union of disjoint sets simply by summing up the individual probabilities. Right? So if this is my omega, right, and I'll have a set in here. This could be F1, and I have another set over here. This is my F2, the disjoint. I want to compute the probability of the union. Okay, that's just going to be summing up the individual two probabilities. Then there's a question about where we are in the course. Well, so the way to keep track of where we are, well, at least roughly, the way to keep track of where we are, at least roughly, is to go on the on Canvas and grab the syllabus. And so we are down here in week number 2. We talked a little bit about multivariate binomial models, and then we're talking about sigma algebras. So there are some sections here to start working on. It's not the case that this class here follows the textbooks line by line. We're not doing that. These here are just references where you can find more information. this material is coming out here. This is not something that you will find necessarily in the references. For example, if you're interested in von Exarchus paradox, I would, instead of reading about von Exarchus paradox, I would just go to YouTube and download a video. And there are lots of them, and so what you do there is you try to explain how you can take this ball and what the sets are that you could be interested in, and breaking them in and reassemble them. So this would that's how I would do it. But yeah, the syllabus has a schedule at the end of it. That's a place to start for West reading in the material. Okay, it's late, and as usual, I'm hungry. So I just want to advertise again that we have office hours on Thursday morning, and we have office hours again on Friday morning. So if you have questions there about the homework or about the lectures, these are good times to come. We have had some activity, but there's always room for more questions. So if there are no more questions tonight, then I bid you all good night. So there's always a question. So now it came up again about email. It depends on what the question is about. If the question is about math, discussing math over email, it just doesn't work. It does not work. It's not that I don't want to sit down and type questions out and read them. This is okay. It just does not work. It creates much more confusion than it's helpful. So this is why I'm available before class for questions, and this is why I have 2 sets of office hours on Thursday and Friday morning. It is much better to ask math questions in real time than it is to sit and write an email. It just doesn't work. Okay, I will get the videos uploaded and get the notes uploaded, and then I hope to see you, some of you at least, on Thursday morning, and then of course on Thursday night we have the lecture. All right, good night, guys.